Hi students, wave propagation in lossy dielectrics. So in this, a lossy dielectric is a medium in which an EM wave loses power as it propagates due to poor conduction. Or in other words, we can say that this medium, it is a partially conducting medium. That means it is an imperfect dielectric or imperfect conductor. So in this case, conductivity is not equal to 0. This medium is a imperfect dielectric or imperfect conducting medium. So some sort of conductivity happens in this lossy dielectric medium. So that is a lossy dielectric medium, and its characteristic is sigma is not equal to 0. Some sort of conductivity happens in this particular type of medium. So in this we have to find the wave propagation in this lossy dielectric medium, and also this derivation for the wave equation, that is we considered as general case for the all kind of mediums. So here we are going to consider a linear isotropic homogeneous lossy dielectric medium that is charge free, that is rho v is equal to 0. So in this particular medium, all surface contains a lossy dielectric, that is some sort of conductivity in the surface may happen, and also it is a charge free region. That means this rho v is equal to 0. For deriving the wave equation in this media, we have to derive from the Maxwell's equation for the time varying field that we already studied. So here we are considering the Maxwell equation. We are going to write in time harmonic fields. That means field vary periodically and sinusoidally with time. So we have to write the Maxwell's equation for the time varying field, that is in the case of time harmonic field. So the Maxwell's equation, we know that in differential form, that is first equation is del dot D is equal to rho v. So here instead of this D, we can substitute in terms of intensity E of S. So E of S means this is a harmonic field, that is field vary periodically and sinusoidally with the time. So that's why we represent it as E of S. So this first equation becomes del dot epsilon E of S is equal to 0. We are substituting the value of D as epsilon E of S. And this is right hand side is 0. So again this equation becomes del dot E of S is equal to 0. So that is equation number 1. Because in this epsilon is not equal to 0, we know that. So this term only del dot ES becomes 0. Second equation is del dot B is equal to 0. So here also we can substitute the value of B in terms of magnetic field intensity H of S. That is del dot mu H of S is equal to 0. And again that becomes del dot H of S is equal to 0. We know that this mu is not equal to 0. So del dot H of S is equal to 0. That is equation number 2. Then our third equation is del cross E is equal to minus dou B by dou T. And in this equation we can substitute, instead of this dou by dou T, we can substitute the term J omega. So the equation becomes del cross E of s will be equal to minus j omega. Instead of b, we are substituting mu h of s. So this equation is 3. Then our fourth equation is del cross h is equal to j plus dou d by dou t. And this equation becomes del cross h of s will be equal to, instead of this j, we can substitute sigma E of s. That is, j is the current density. This current density can be represented as sigma E of s. That plus dou d by dou t, that becomes j omega into, instead of d, we can substitute epsilon E of s. So again this equation becomes del cross h of s is equal to sigma plus j omega epsilon, and E of s we are taking outside of this bracket. So this is equation number 4. So all these 3, 1, 2, 3 and 4 equation will be for the time harmonic field. Now instead of, now in order to derive wave equation, we have to consider the third equation. Third equation is del cross E of s will be equal to minus j omega mu h of s. This is our equation number 3. Now we are going to taking curl on both sides. Curl on both sides of equation 3. Now that becomes del cross. If we are taking curl, means it is del cross E of s. That is equal to minus j omega mu. This right hand side also we are taking curl. So it becomes del cross h of s. So keep it as equation number 5. Now if we apply the vector identity, applying the vector identity, that is del cross A is equal to del into del dot A minus del square A. So if we apply this vector identity to this equation number 5, so in this A means here in the equation number 5 is A, that is E of s. So our equation number 5 becomes del cross E of s becomes equal to, if we apply the identity to the left hand side of the equation number 5, this del cross E of s can be written as del into del dot E of s minus del square E of s. This is the left hand side of the equation number 5. Left hand side of equation number 5 is del cross E of s is equal to del into del dot E of s minus del square E of s. And this equation again can be written as, equation number 5 again can be written as del into del dot E of s minus del square E of s will be equal to the right hand side of this equation, 5, that becomes minus j omega mu into, instead of this del cross hs, we can written as, that is from equation number 4, that is del cross hs is from equation number 4, that is sigma plus j omega epsilon E of s. So we are going to substitute the value of del cross E of h, del cross h of s here. So it is sigma plus j omega epsilon into E of s. Now we know that from equation number 1, this del dot E of s is equal to 0. So this is del dot E of s, this becomes 0. So now again this equation can be written as del square E of s will be equal to j omega mu into sigma plus j omega epsilon E of s. This equation can be written as del square E of s minus gamma square E of s is equal to 0. That is equation number 6. This gamma square is this term. This term we can take it as gamma square. So that is gamma square is equal to j omega mu into sigma plus j omega epsilon. That is equation number 7. And this gamma means it is the propagation constant of this medium. Propagation constant of the medium. And similarly, we can derive for H field also. So this equation finally becomes del square H of s minus gamma square H of s is equal to 0. That is equation number 8. And this is equation number 6. This is equation number 8. These two equations, that is equation 6 and equation 8, are known as vector wave equations. Vector wave equations or Helmholtz equations. Helmholtz equations. Now again, if the wave propagates along z direction, E and H do not vary with x and y. We know that if the wave is propagating along z direction, so there is no component of the electric and magnetic field. So in that, electric and magnetic field does not vary with the x and y. So in this, only the z component of the wave is only varying, not varying the x and y. So we can say that this dou by dou x is equal to dou by dou y is equal to 0. And now again from equation 6, that is from our vector wave equation, from equation 6, del square E of s minus gamma square E of s is equal to 0. In this, if we take, we are taking this E of s is equal to Exs Ax plus Eys Ay plus Ezs Az. We substitute the value of this Es here we can write instead of this del square. This del square we know that in Cartesian coordinate system it is del square mean it is dou square by dou x square plus dou square by dou y square plus dou square by dou z square. So we can write that from equation 6. Again we can write that dou square by dou x square plus dou square by dou y square plus dou square by dou z square minus gamma square into, instead of this e of s we can write as exs ax plus eys ay plus ezs az is equal to 0. Now we know that this dou by dou x is equal to dou by dou y is equal to 0. We can say that dou square by dou x square which is equal to dou square by dou y square which is equal to 0. So these two becomes 0. So this equation becomes, we can again written as, and also if we consider a plane wave, consider a plane wave that has only x component, that has only x component of E and propagate along z direction. So we can write it as, this equation becomes, we can write it as dou square d square by dz square minus gamma square into exs of z, that is equal to 0. That is, we are only considering the x component of E. And here we are taking the d square by dz square because here only varying dz component. So we can take it as d square by dz square, not the dou square by dou z square. And this is the vector wave equation. This is a wave equation. This is the wave equation. Equation for a lossy dielectric medium. Lossy dielectric medium. So this is very important, this derivation. Up to this, if the question is asking for the derive the wave equation for a particular lossy dielectric medium, so we have to derive from the Maxwell equation to up to this. And this is a general case for different kind of medium, like our lossless medium, good conductor, free space medium. The same procedure will be the same like this, but the in the other types of medium, the characteristics of that particular medium we have to apply, but the procedure is same. And this is our general case for deriving the wave equations.